Hello everyone, so this is the second video on the CPSolving series, which basically has the objective of solving CP problems, presenting the problem itself, the solution, and the coding part for the problem. And for today's video, we will be solving problem E, which is part of the AtCoder beginner contest 174. So let's go. This problem is called logs, and the statement basically say that we have n logs, each one with length ai, so from a1, a2 until an. And for those who don't know, a log is basically a chunk of wood, and the problem say that we can cut these logs at most k times in total. And when a log of length l is cut at some point whose distance from an end of the log is t, then it will become 2 logs of length t and 2 logs of length element t. So for example, if we see that log as a rectangle, so this rectangle will have some initial length, would be like, can be like 10 or something like that. So we can come here and just make a cut that it's not on the border of the log. So after that, we would have now 2 logs, so this log here and then this log here, and each one of them would have now new lengths. So for example, it could be like length 9 here and this one with length 1. So basically the problem says that we can take any of these logs and could then in some point that we want to, as long as these points are not on the borders of the log. So we want to have 2 logs that have at least length greater than 0. Okay, so we can do this cut these logs, and we want to find the shortest possible length of the longest log after at most k cuts. These cuts can, the logs after a cut can have floating point values. So for example, we could, instead of being 9 here, we could actually make it like 9.5, and here we would have 0.5. so there is no need to the resulting lengths to be integers, but the problem asks that after all of these cuts the answer be an integer. So if the answer is a floating point, then we'll round this up to an integer. So okay, so let's understand what this means exactly. So just let me erase all of this. So we will have like a lot of logs here with not necessarily the same length, and we have available k cuts that we can make in any of these logs, and also in the resulting logs after the cuts. And after those at the most k cuts, we want to have we want that the maximum length log has the shortest possible length. So for example, let's say that we have 2 cuts, and then we have those long logs, and then let's say that this log here has length 5, this here has 10, this here 3, and this here 15. Then we have 2 cuts. So what we could do was, I don't know if this is actually the optimal answer, but something like that, just to illustrate the problem. We could this guy here in the half, and then this guy here in the half. Then we would have like a new log here with length 5, a new log here with length 5 also, log with length 7.5 and another one with 7.52. And for this case, the maximum length log, which is this one or this one, have length 7.5. So the answer for the problem, supposing this is the optimal answer, I don't know if it's actually the optimal one, would be 7.5. And as they want us to round it up, then we would print 8, that's the nearest integer to 7.5. So for example, in this case here, we have 2 logs and we can make up to 3 cuts, and each log, the first log has length 7 and the second one 9. So in this case, we can cut the first log of length 7 in the mid, so we would have 2 logs of length 3.5, and next we could cut the log of length 9. At some point that would result in a log of length 3, and then we would have the other side with length 6, and then we could the log of length 6 to have the 3.3 and 2.7, and then the maximum logs would be this one or this one, and both have 3 point something, would be rounded up to 4 later. So okay, so how to solve this problem? Before I jump into the solution or some thinking, the constraints for the problem are: we have at most 2 multiplied by 10 up to the 5n logs. We have at most 10 to the power of 9 cuts, and the lengths of the logs can go up to 10 to the power of 9. So we can see that the number of cuts is very high, so simulating all of them could be dangerous if we take some naive approach. Yes, I think those are the observations. We can do probably something linear with this n, or something n log n squared root n, or something like that. So by looking at this problem initially, we can try to have some naive approach that might work or not. So let's say if we try some grid approach or grid algorithm, we can try to get the largest log initially, and then try to make some cut around it. So for example, we could try to make some cut here, and then we would think, oh, okay, I have more cuts available. What is the next longest log? So we could try to make some cut here, but this eventually, the thing here is that we don't know actually where to make the cuts. So for example, in the first example here, the question is it optimal to make this cut on the half, or is it optimal to make the cut here? So these questions are kind of hard to answer, because for example, if I make the cut here in the middle, and I have more 10 cuts to make, I can't know for sure if this decision here was good, because for example, I could do a cut here and then a cut here would actually give me a better answer after all. But I don't know these points exactly, so it's kind of hard to try to know actually which log to focus on firstly, and actually to know in which point to make the cut firstly. So I think it's hard to think in these problems like this. So it seems like a very open problem. You have too much variables that you need to take care of, and when this happens, it makes sense to try to understand the problem in another way, or try to fix some of the variables to make the problem smaller, and then you solve this smaller instance and then solve the bigger instance. So, but I think for this problem we want to try to rephrase it in another way. So the current phrasing for the problem is we want to find the shortest possible length of the longest log after at most k cuts. So, but instead of asking this question, we can think about this in the following way. So, what's the minimal number of cuts to make all logs have at most length t? So for example, let's say that we have chosen some integer t that we want to make it the largest value after we make some cuts. And then for this t that we have chosen, we want to find out how many cuts, what's the minimum number of cuts, let's say c, that you can have after making these cuts. After in such a way that all the logs have at most value t. So for example, let's say that I have chosen t with 4. So in this case, I need to make cuts in some way that I will minimize the number of cuts I make, and every log after those cuts needs to have at most length 4. So for this case here, for example, for this log here, I could just make a cut here, and then assume that this part would have length 4 and this part would have length 1. So for this log here, I could make 2 cuts. It would have like length 4 here, length 4 here, and then length 4 2. Here I don't need to make any cut because it's already under our limit t. And here I could make like a cut here, and then here, and then here, and then I could have like 4 4 4 and 3. Let's say that despite being larger, visually it's length 3. So in this case, let's assume that these cuts were made in the optimal way. Then we have 6 cuts. So we needed 6 cuts to make that all of our logs have length at most 4. So then the minimum number of cuts would be 6. So now let's imagine that we have built some function f that received this limit t that we have set, and then returns this minimum number of cuts in order to make all the logs have length at most t. In this case, if all the logs have length at most t, then the longest one absolutely has length at most t. So okay, let's say that we have this function f. So one way to solve the problem is basically to iterate through all possible values of t, and then find the smallest one such that c is smaller than or k. Because if we find some value that needs less cuts than k, less or equal cuts than k, and this value is the smallest possible, then this is the answer. Okay, so one possible way would be to, okay, let's say that we want that the longest log has length 1 after all the cuts. So we take f and call it for 1, and then let's say that would give us 30, but k is 10. So we know that 1 in this case can be an answer. So the length 1 for the longest log can be an answer because we need more cuts than the allowed. Okay, so we can try now f2, and this would give us like 20. We know, okay, 2 is not an answer because we need more cuts than allowed. And then we can try every element, every value, until we find the smallest one, which give us the minimum, the number of cuts below the allowed case. So in this case, for example, it would be 5. So we iterate through all the possible values, which should be from 1 until the largest value of log, the length of log, and then the first one we would stop. The first one that's below k would stop. So in this case here, the answer would be 5. But given that we can go up to 10 to the power of 9, for example, supposing that we have just one cut, this can happen if we have a lot of logs of this length, then we would iterate from 1 to this value here, and it's pretty expensive computationally to do that, so it would probably not be able to pass this in time. So we need some smarter way to iterate through all these values without actually passing through all of them. So for example, one observation that we need to make in order to improve this solution is that every time we increase this value that we are passing here, the the number of cuts gets smaller. So for example, because if you want to make all the logs have length at most 1, then making all the logs have length at most 2 is probably easier. That is, we need less cuts than if you want to their lengths to be 1, because this condition here is already contained inside this one, and this one here is already contained inside this one, and so on. So if we draw some graphic where the x-axis is the limit t that we are choosing for the logs to have length, and here is the return of the function ft, then the function, the graph will look something like that, or at least it will be decreasing. So it will never increase again, because we can be sure that a value greater than some other value won't need more cuts than the last one. So this gives us a interesting property, because we actually can, let's say, know what will happen. So for a given value here, we know that all of the values before this one are actually greater than or equal this value, and every value t after that have ft greater than less than this value here. So this property that a function that actually go always down, or like never go into directions, like always decreasing or always increasing, something like that. Functions like this that always increase or always decrease are called monotonic functions. That is, they have only one direction, if I may. And these functions, they can be binary searched. So you can make binary search in these functions. And these are a very cool thing that allow us to improve the speed of our algorithms to find the optimal point that we want in these functions. So basically, what we want to find here is the point such that the value of is the smallest value of t such that the value of ft is below some threshold. So let's say that we have the value k here, and then what we want to find here is this point, because it's the smallest t that's below or equal this threshold. So how do we binary search? So basically, as said, we need to have a function that always decrease or stay still and then decrease, or always increase. We can have a function like this that will increase and then decrease and then increase, then decrease, and so on. We always need the same direction. So we'll have a function like this that will always decrease, and for the binary search always has two endpoints. So we define the left endpoint and the right endpoint, and these endpoints will tell us where to search for the optimal value. So initially we put some values on these variables, and then we know that the answer is surely between these values. So what we do is we take the mid value between this range, so let's say here, and then we evaluate the value of ft. So let's say that we have the threshold decay here, so all the points below this line would be able to be the answer because they need less cuts than we have, but we want the smallest one, so the point that we actually want is here. But we have just tried this value because this is in the middle of the range, and so we choose this point, then we evaluate it in f, and then we'll have some answer x. So what we do is we compare x with k. So x is the number of cuts needed to have at most I length for the logs, and as x is smaller than k, we know that the answer is not to the right of this point, because this guy here is already less than k, and we know that from to the right of this guy on, the answer will always decrease. So we need to go to the left to try some increasing, and going to the left we will actually choose some smaller points than the current one. So we know that all the values here are useless from now on. So what we do is we take our r and put it here, and we have a new range which has half the size of the previous range, and then we do this process again. So so we try the midpoint of the range, so let's say here, and we say, oh, this point here evaluates some value that's yet smaller than k. So we know that the answer is to the left of this point. So we make r equals to this point here, and then we try again the midpoint, so we'll try here. So we see now, oh, this point here evaluates has a value x greater than k, the value. So in this case we know that the answer is to the right of this point. So in this case we make the L here, and then we have a new range again. And we keep doing this until the range has size less than 1. So when we have that L is greater than R, then we know that the search has finished. And then the complexity of this approach is basically we have some initial range, LR, and for each iteration we make this range have length half of the previous range. So in this case, if the initial range has length R minus L, then the complexity until this range becomes with size 0 is O of, log of R minus L, because we can halve the length of this range at most log R minus L times. So we will always halve it. Okay. So we could use binary search in this problem. Now we only need to know how to evaluate f. So given some limit t, how do we return the minimum number of cuts needed to make all the logs have length at most t? So for that I would show you this in code. So let's try to code it. So the first thing here is to declare the variables. We will need n and k, and also need some array. So this array can have length 2 multiplied by 10 to the power of 5. Now I like to declare this globally. So we read these integers. And now this is how we do binary search. So first we need to set the values for the variables L and R that I have set, which will be our range on the binary search. So for this case we need to think what are the values that for sure the answer is between them. So if you think about this problem, we know that every log needs to have length at least 1, because we can't cut a log into such a way that one of them has length 0. So we know that all the logs, independent of the cuts we make, will have at least length 1. So we can say that these are lower bound for the binary search. And we also know that the logs will have at most value 10 to the power of 9. So I think it's a good upper bound too. So we have set our limits for the binary search, and we will also declare some variable which will be our answer. So I like to declare it with some invalid value, so I can't have an answer which will have value -1, so I can use this later as a debugger or something like that. And then the condition for the binary search is just to look for the answer while this range has length more than 0, while this range is valid. So so the first thing is to find out what point we want to look at, which is the midpoint, because this is optimal because we are always decreasing the value of the largest range that we are cutting then. So to find the midpoint, basically we find the midpoint of the range, which can be left plus right minus left, which is the range of the length of the range divided by 2. So what we are basically doing is we take some range, LR, okay, so I won't be able to draw here, just let me. So okay, I have this range LR, and then I want to find this point here. So basically, if I take this variable L and sum the half of the range, then I arrive at this point, and the length of the range is basically R minus L, and if I divide this by 2, I have half the length. So this is what we do. You might encounter in some codes something like that. So right plus left divided by 2. But this can be dangerous because sometimes your limits can be high and this operation here can overflow. So it can be that, I don't know, your limit is like 2 to the power of 9, and then if you sum these two, you have an overflow. This operation here is overflow safe, and I recommend using it over this one because I already had problems with this one. So okay, so what we do now is we'll make some function that will tell us whether this value is okay. So this value here, mid, is our limit for the maximum log length, and if this value is under the threshold of k, then it's a valid value, and after that we set the right endpoint as mid minus 1, because we don't need to look at mid anymore because we already have looked at it, and then we want to, the range will become actually left and mid minus 1, and we know that the answer might be here, so we look at it, and as we know that the answer is okay here, we set it as the answer. So if eventually there is a better option for this as an answer, then we enter again this if, and then the answer will be set for this better option. So we know that we don't need to be afraid that the actual answer will be overridden. So if it's not okay, this value, if it's the number of cuts needed is greater than k, then we need to actually make the range go to the right. So we do this because we use mid plus 1 because we already know that mid is bad, it hasn't helped us, so we now set the range to mid plus 1 right, and here I will just left mid minus 1. So after these operations we would have the answer. I like to use an assert here to check whether the final value is this invalid value I put here, because in theory after this while I need to have ends with some valid value, and if it's not, then I have some logic error and I want to catch that in some runtime error. So this is a trick to use, because if you do not have this assert, then you could have wrong answer and not know if you have a logic error or a solution error. So you don't know if your problem is in the code or on your idea. Okay, so now we need to code this function okay to be basically receiving some limit and then returning whether the cuts needed function, which is our f function that we have set here, will give us less cuts than the threshold. So if the cuts needed for this limit is below or equal k, then we know that it's a good limit. So now we just need to code cuts needed. So the idea here is basically given that we want every log to have at the most length limit, what's the minimum number of cuts to make that happen? So we can have some variable cuts, and basically we iterate through all of the initial logs. And the optimal way to make cuts here is to, okay, so just let me erase all of this. So okay, so let's say that we have a log here of length 17, and then we have our limit or t as 4. So we want all of our ending logs to have length at most 4. And what's the optimal way to make cuts here in order to minimize the number of cuts? So an initial idea would be cutting this thing in the half, and then checking if it's not enough, then cutting half again, then cutting half again. But okay, so let's say that this, after all of these cuts, this guy here has length 3.8, this guy 3.8, and this guy 3.8, I don't know. Okay, so let me do it correctly. Forget everything I said about these values here down there. I just want to know how much is 17 divided by 4. Okay. So okay, so after these 3 cuts, we could have like 4.25. Which would not be enough. So we would need to make a cut here again, and then here again, and then here again, and then here again. Would leave us with like 1, 2, 3, 4, 5, 6, 7 cuts, which seem to be too much. So in this case here, we like have a size here with 2.125 length, but we actually can like take this cut here and bring it to the right. So we want to maximize the length of this first part, because if we bring this cut here to here, then we can bring this cut here to here, and this here to here, and then so on. And all of these guys here, they will be discarded. So actually the optimal way to make a cut in some initial log is to take this limit and then take exactly the length of this limit and make a cut. So let's suppose that this part here has length t, and then we come again and find another part of length t and make a cut here, and then so on. So in this case, if we have some length like n here, then the number of cuts needed to make all of these logs have length less than or equal t is actually n divided by t. So this will give us let me think. So n divided by t will give us the number of length of logs of length t after we make these optimal cuts and some rest. So in this case, if we make 17 divided by 4, then we'll have something like, let me see, 4.25. So we have 4 parts of length t, and imagine that this part here has length 0.25. So in this case, we can, if we round up this value, we actually have 5 parts with length less than or equal to t. And as we have 5 parts, we know that 4 things separate these 5 parts. So we actually need to find how many parts are there with length less than or equal to t, and then the number of cuts is just this number minus 1. So basically we want to calculate how many parts are there, which is basically the length of the current log divided by the limit, and number of cuts is basically parts minus 1, which is what we have seen here. So for this count here, we actually need to round up the value as we have set here, because although we have 4.25, we want the number of parts to be 5 because there is this rest. And for doing this operation of rounding up a value, when we do integer division, we can do that by actually summing the down part with it plus 1. So for example, let's say that we want to make the division a over b, and this is an integer division, both a and b are integers, and we want to round this up in case we have some rest. So for example, if I have a equals 7, b equals 4, then if I do a over b, it would be 7 over 4, which would give us like 1.75, and as it's an integer division, it would give us actually 1. But we want to round this value up without passing this value here to some function or something like that. So to do that, we can basically, instead of doing a over b, we do a plus b minus 1 over b, and this will round up in case we have some rest. So one way to think about this is, if a is a multiple of b, so if a is like b multiplied by some bk, then we won't have some rest, because it would be like b multiplied with k divided by b. And in this case here, if we sum b minus 1, then we will not reach the next multiple of b, which would be b plus b multiplied with k plus 1, because we would need this value here to be b actually instead of b minus 1. So this value here would not change it, that is, it will not round up, and that's what we want, because this has no rest. And in case a is not a multiple of b, then this value here will actually make us pass to the another multiple of b. So for example, if a is between b multiplied by k plus 1 and this is the open interval, and b plus multiply with k plus 1. Then if we sum this value here with b minus 1, we with certainty we'll pass this value here, and then we'll have the value round up. So this is the reason, and I think this should be the answer for the problem. So okay, it's compiling, so we can test some case. Okay, it seems okay. We can try some edge case, like having no cuts at all. For example, 1, 10, 100. Oh, okay, I forgot. So I have 3 logs, 0 cuts, and lengths. 1, 10, 100 would be 100 because we can't cut anything, and this is the largest one. We can try some overflow things, like trying the greatest value. Okay, so we can actually try more tests, but for the sake of this problem, I think it's okay. I recommend doing a lot of tests before sending your problem, your solution. So okay, so I think it's clear how binary search and how trying to formulate the problem in another way were helpful here. And if you have any doubt, you can leave in the comments that I will happily answer them. So bye bye, thanks for the views, bye bye.